All right. So can the people in Zoom hear me? How about Andrew Wee? Can you hear me? Very good. Right. So this is the penultimate lecture, which is very sad, but nevertheless, we will make use of whatever time we have to learn whatever remaining stuff we have. Okay, and I will do a demo to show you some really cool stuff about the central limit theorem very shortly. But before that, let us recap this very important two concepts from section 4.3, which you should read. Is it 4.3 or 4.4? I'm not very sure, but it's one of those sections, okay? So there are two concepts here. We are given two random variables, okay? These are correlated random variables, not independent. X, Y have joint PDF given by fxy, okay? So they have a joint PDF, and then we know what is the meaning, or hopefully you by now you know what's the meaning of expected value of x given y equals to y. Well, that is nothing but the expectation with respect to the conditional PDF of x given y, dx here, yeah. Okay, so that is the conditional expectation given a particular event, because a random variable y takes on a particular value little y. Okay, and what we are integrating is we are integrating against this particular distribution, which is conditioned on little y. Okay, so the conditional expectation as a random variable, when you're conditioning on a particular random variable y, this is the random variable that takes on the value, expectation value of x given y equals to y whenever, okay, I cannot spell, whenever y is equal to y. And today we will do a few more examples, but I don't want to do an infinite number of examples, okay? So this is a particular random variable that takes on the value, expected value of x given y equals to y, which I've already defined above, whenever y equals to y, all right? Now we have a similar notion of the variance, okay? So the variance of x given y equals to y is the integral of x minus the conditional expectation conditioned on y equals to y, quantity squared fx given y, x given y, dx, okay? And variance of x given y is in fact the random variable that takes on the value given by the conditional variance whenever y is equal to y. So I just have to adjust this a little bit, okay? So it's completely analogous, as you can see here. Okay, so the law of iterated expectations or total expectations, iterated expectations, is something that we have to commit to memory. That means we recover the expected value of x when we take the expected value of x given y here. Okay, and the law of total variance is more complicated. This is something I talked about last time, and it can be expressed as follows. The variance of x is the expectation of the variance of x given y, which itself is a random variable, plus the variance of the expectation. Okay, so these are two formulas that we should commit to memory. Okay, now, so let me briefly talk about this particular example. Okay, let me see. What is a good example? Maybe we talk about this one first, okay? They are all almost the same. All right, so we can compute variance by conditioning, all right? So I'm going to talk about maybe 2 or 3 examples, then we'll talk about the central limit theorem, in which we will start off with a demo. Okay, so this example says the following. Computing variances by conditioning. And then the above quantities will become self-evident. Self-evident means obvious, all right? So we have a particular PDF, which looks a bit strange, but it's nicely split into 2 parts, okay? So as you can see here, the PDF is 1, 2, 3, and this is fx of x, that is x, and it takes the following form, Okay, this is going to be half. And this is going to be how much? A quarter. Okay. So before we do anything else, Sean, what should we do? When I tell you that this is a PDF, will you believe me? No, unless you. Yeah, can we check quickly? Well, this part has area half because half times 1. And then here we have 2 times a quarter, which is half again. Half plus half is exactly 1. So I'm not lying. Okay, so this is indeed a PDF. We always have to do this check. Okay, otherwise the question is not good. So now what we have is we have a correlated random variable y. Correlated means not independent with x. 1, 2, when x is less than 1 and when x is bigger than 1. So the correlatedness comes about from the fact that if I know that x is less than 1, that means x lives here, then the random variable y definitely takes on the value 1. If x turns out to be here, the random variable y takes on the value 2. Okay, so now I'm interested to compute. We want the variance of x. Okay, so suppose you didn't know this special formula, the law of total variance. You can do your integration and do something, you know, to go and find the variance. But that's not the point here. We want to do this in a quick and easy and fast method by using the law of total variance. Okay, so as you know, if we want to use the law of total variance, we need to prepare the ingredients in order to cook this dish. All right, so we want to cook this. We need to prepare a few things. We need to prepare this random variable and we need to prepare this random variable. We need to prepare them properly, then we plug it inside. Understand? This is what I did last time as well. We prepare all these random variables properly. So it is easier to prepare this first. What is the meaning of expected value of x given y? Okay, well, how many values can y take on? Y can only take on 2 values, namely 1 or 2. So what is this? Say this one here. This is nothing but expected value of x given that x is less than 1. Okay, let's call on people in the Zoom. Now, if I know that x is less than 1 from the picture, what is the expected value of x? How about Andrew? I know that x is between 0 and 1. What is his expectation? Okay, someone can help Andrew. How about? Thank you. Okay, half. Thank you very much. Next one, we let someone in the Zoom help. Y equals to 2. So that is nothing but the expectation value of x given that x is bigger than or equal to 1. So how about Deng Jie? So how about Deng Jie? So now our x is in this region. Okay. So what do you think is his expectation? We are restricting ourselves to this region here. Okay, anyone in the Zoom wants to help? Okay, anyone in the class wants to help? 2. Very good. Okay, so we can actually write down, so if we let z be the random variable expected value of x given y, without conditioning on particular values of y, let us now write down what is the PMF of z. The PMF of z is given by P of ZZ equals to, well, with probability half, Z is equal to half. Okay, why? You look at this sentence properly. This is the random variable that takes on this value whenever y takes on value y. So what is the chance that y takes on the value 1? What is the probability that y takes on the value 1? It's the probability that x is less than 1. That probability is exactly half. Okay, so with probability half, the value of z is half, this half here. With probability half, the value of z is 2. So that is the probability mass function of the conditional expectation. I know this is a bit difficult to get your head around, but you have to get your head around this. Okay, so we have prepared this particular random variable. We have prepared it, we have actually written the probability mass function down. Does everyone understand this last thing here? The book is too fast. This is an example from the book, okay? Anyone has any questions on this part here? So I just want to, there are too many halves happening here. This half is this half. Okay, this 2 is this 2. This half, say this half here, is actually this probability. There are too many halves that you may be confused by. And the remaining half, this brown half, is this half here. What half? This, okay, exactly. Oh my gosh, you are so smart. This is the, oh man. This is, I'm also confused, right? This is the half, okay? And then this is 2. This is half here. And then the gray color, this is the remaining half. Thank you very much. So everyone understands where the half and the 2 comes from? I think this is very clear now with all the colors. Okay, so with probability, this mentions the with probability half, z is equal to half. Comes from here. Because x less than 1, y equals to 1. Okay, right. With probability half, z is 2. What is z? Z is the value of the conditional expectation. This number here. This number half is here. So this is z. Everyone understands? Okay, so we can prepare a few more things. Okay, I want to make sure everyone understands this. It's super important. The book is very fast here. Okay, so we do the same. Let's consider the variance of x given y equals to 1. That is the variance of x given x less than 1. Okay, so now we are restricting ourselves to this particular interval here. What is the variance of this particular random variable when x is restricted to x less than 1? It is uniform on 0, 1. This is uniform. So if I know that x is less than 1, it must be uniform on 0 to 1. So what is its variance? Does anyone remember? What is the something? B minus A over 12. What is B? What is A? Very good. So 1 minus 0 squared over 12. I'm just going to write 1 over 12. Very good. Everyone understands. So now we are going to consider the other value of y. Okay. So the other value of y is 2. Here is bigger than this, not okay. So this is 2, and this is bigger than. And so now we refer again to the picture. Okay. So now we are x bigger than 1. So we are living in this space here. So the PDF of x condition on us living in this space is definitely uniform. And uniform from where? 1 to 3. So what is its variance? Well, someone there told me the general formula of b minus a squared over 12. So we have to figure out what is the b and what's the a. This is the b and that is the a. Right? So it's 3 minus 1 squared over 12. So this is 1/3. So if I let, say, w be the random variable variance of x given y, then I can write down the PMF of w, okay? Then the PMF of w is going to be given by the below. Then the PMF of w is this one. Oh, I'm sorry. Two values. Again, half, but w takes on the value 1/12 and w takes on the value 1/3. And this one comes from here, the probability of this part, this one comes from here. And now this one, this 1/12 comes from here, and 1/3 comes from here. Okay, so we have now the PMFs of the conditional expectation and the conditional variance. So now we have to refer to this particular formula. Okay, so we have to plug these inside. Okay. Right. Now we keep note that we have to use this formula here. So we have two parts to tackle. Let's tackle the second part first. The variance of expectation value of x given y. I gave this a name. That was the variance of z, right? So z has this particular PMF. So it's not too difficult to figure out what's the variance. Okay. Now, if we have this PMF, the expectation of z is what? Okay, it's 1 over 2 times 1 over 2 plus 1 over 2 times 2. And this is equal to 5 over 4. All right, so the variance is going to be half times half minus 5 over 4 squared plus half of 2 minus 5 over 4 squared. That's the formula for the variance. You take the mean, you take the number minus the mean, squared, and then average. Okay, so this is some number that we are going to write down very soon. If I look at my notes, I figure out that this number is equal to 9 over 16. All right, so now we need to, you see, now I've tackled this part here. This part here, I have computed it to be this part here in purple. All right, so we have another part to tackle, which is the first part. And that is the expectation of the variance random variable, x given y. But that's nothing but the expectation over w, right? Which is this particular random variable. Okay. So that would be given to us by, just take the expectation of this PMF. How difficult is it? Half times 1 over 12 plus half times 1 over 3. That's the expectation of the w. And after you're said and done, this is 5 over 24. Right? So this is 48, 48, 16. Yeah, correct. So this one here, this here is this part here. All right. So basically we have these two parts that we need to sum up, and we can sum them up. We can sum them up by just typing onto our calculator, or better still, using your mental sums. Okay, so this is going to be 37 over 48. Okay. So as you can see here, this example is very nice because it tells us exactly what all the definitions are. Okay, we first look at the expectation value of x given y equals to 1. And I think someone there mentioned that if I restrict my attention to y equals to 1, that is x less than 1, then we are uniform on 0, 1. And so our expectation is in the middle. That justifies this. If I'm in the other part here, then my expectation is exactly here at 2. Okay. So that is the conditional expectation random variable summarized into this particular PMF. And it's a PMF because it is discrete. They can only take on 2 values. We can easily calculate the expectation, okay? And we calculate the variance, its variance, by using this particular formula. This formula is actually expectation of z minus expectation value of z quantity squared. Okay? So basically, I have the averaging here. I have the value z minus the expectation, averaging the z value minus the expectation. Here. And you get some number. For the variance part, we can compute the definition of the conditional variance, and the conditional variance takes this form. And here we mentally remember that the variance of a uniform random variable is b minus a squared over 12. And here we have to just take care of the b minus a squared is 1. Here b minus a squared is 2. And that's why we have this 1 and this 2 here. All right. So the variances can only take on 2 values, 1 over 12 and 1/3. And they are summarized in this PMF here. Because x less than 1 has probability half. X bigger than 1 has probability half. Okay. So that is basically the PMF of the conditional variance. And we are required to take its expectation. And we take its expectation here. And we add up the 2 parts, we get this. Okay. Any questions? Andrew, any questions? All right. If not, let us do our example. Yeah. Variance of Z. There's no variance of Z. It's variance of W. Also variance of Z here. Variance of Z. Okay. Right. Let me do this calculation a little bit slower. Sorry, now I'm confused. Oh, variance of Z is here. Okay. Right. Let me go through the variance of Z more slowly. Okay, no problem. Okay. So the variance of Z can be written as expectation of Z minus expectation value of Z quantity squared. But we recall that the PMF of Z is the following. So we bring it down here. Okay. All right. So what do we need in order to compute the variance of Z? Okay, there are two ways of doing it. I did it the unconventional way. Okay, I did it the unconventional way. Let's do it the conventional way if you wish. Okay, so you can do expectation value of the basic second moment. I think Sean is very familiar with this way, so we'll do it this way. Okay, so the expectation value of Z here is basically half times half plus half times 2. This is 5/4. Okay, so you have this is 5/4 squared. Okay, can? All right, so the first moment requires the second moment requires a little bit more work. The second moment, just look at the PMF here. You are required to square this, half squared multiplied by half plus 2 squared multiplied by half. So that's 2 plus 1, 17/8. So this is 17/8 minus this one. Okay, so this is, let's see whether this other method yields the same answer or not. So this is 34/25, 34/16, 9/16. Is it the same as just now? Yeah. So this first method that was shown in the book, right, is a bit unconventional because we are using this formula. But now I use the formula that you are more familiar with, I get the same number. Okay, is this clear? But you must know where this Z comes from. This is the conditional expectation random variable. Okay, so Liao Xue, I use two methods. Sorry, this Andrew is blocking you. Okay, is this clear? Right. So I want to go through one final example before we talk about the central limit theorem. Okay. So, any other questions here? I think this variance calculation is a little bit difficult. The rest is okay. All right. So, example. All right. We have n students. N being capital letter here, right? It means that it's random. Because every time a random number of people show up, n students show up to LT7 each time. And the PMF of the students is Pn n equals to 1/10, 9/10, n minus 1. It's geometric. This is a name. It's called geometric random variable. So potentially, right, I could have 1 million students show up because the support of the geometric is unbounded here. Potentially, I could have 1 million students showing up, but that's not very likely. Okay, so this is called a geometric PMF with mean 10. The mean is 10. Okay, if you do not know why the mean is 10, you can look up Wikipedia. All right, if you still do not know, you can come and ask me again. But that's not the point of our discussion here today. All right, now if a student comes, he brings XI dollars with her. Okay, so everyone brings a random amount of money. And from our past experience, from this class and from me looking at all your wallets, I know that the mean of the amount of money you bring is 7, just like last time. But now I have an additional piece of information that I need. in order to carry out this calculation, and that's the variance of xi is equal to some random number, 6. Okay, I came out with this example. So the question is, find the mean and variance of the total amount of money brought to LT7. Of total amount of money. So as you can see here, right, there are 2 levels of randomness. One is actually the more students come, the more money I will have in the lecture theater. But there's another source of randomness because, okay, suppose one person comes, there's still randomness because the person is bringing a random amount of money that is around 7 and has a spread of square root 6. The spread is a standard deviation. Understand? So there's the 2 sources of randomness, okay? So we are interested in the S, which is equal to x1 plus x2 plus ... plus x capital N. The number of terms in this sum is random. It's capital N. Number of terms is random, okay? So when we want to compute the expectation and the variance of this guy here, we need to prepare some statistics. We need to prepare some numbers. This is not in the book. I think it's in the book, but then the story here is not in the book. Okay, so you either copy or you just listen. All right. So here, what we are interested in is to compute the variance of S. We're going to find the mean. Last time I found the mean, so I'm not going to do it again. Now we're going to find the variance. Okay. So we have to prepare expected value of S given n equals to little n. So that will be expected value. Oh, I forgot to say something. I forgot to say one very important thing, and that is let me move this down. Okay, we are going to assume, because if we don't make this assumption, we cannot do the calculation. Assume the xi's are independent of one another. So how much money Valencia brings is independent of how much money we get brings, and they're independent of one another and independent of the random variable representing the number of people who come to the lecture theater. Okay, so they are independent of one another and independent of n. Okay, so now we want to do this calculation, prepare these statistics. Right, so expectation value of S given n equals to n. So we have x1 ... plus xn. That is just the definition of S. Okay, but this is equal to, well, I know for sure I'm conditioning that n is little n, so I put n here. And by the fact that capital N is independent of all the xi's, I can drop this guy here because of independence. So I have just x1 plus ... plus xn. And this is nothing but n times of the first expectation, which is 7n. Is that clear? Actually, we did a calculation like this previously in the context of conditional expectation. Hence, we have that the expectation of S given n is equal to 7n, capital N. Is that clear? We did this before. So now I first fix the number of people who come. I call that little n. I know that little n people come. So what is the expected amount of money that they bring? 7n. Okay. What is more difficult is the variance of S given n equals to n. So that is the variance of x1 plus xn given that capital N is equal to little n. But this is actually very similar because I know that n people come, little n people come is no longer random. So I can de-randomize this. Okay, so I know that 9 people came to today's lecture. So n here is 9. So I can fix this to be 9. I fix this to be 9. Okay, everywhere 9. Okay, but generally n. Okay, but now the x1s to xn's, they are independent of the n. So we can basically just drop the last event here. Drop this, I don't like this because it's independent of the x's. So I have this. Now, what can we use? Variance of the sum. And I said that the amount of money that say Hadrian brings is independent of the money that Oliver brings. So once you have independence, what can you say about the variances? The variance of x1 plus x2 is what? Huh? They add up together. So this becomes variance of x1 plus ... plus variance of xn. So what are the individual variances? Well, we know it's 6, right? 6 for every I. So this is 6n. So more generally, variance of S given random variable n is 6 capital N. Is that clear? All right, so basically the whole procedure is to de-randomize. The problem is I do not know who shows up. So I assume that 9 people show up first, little n people show up. Then we can compute the variance in a very nice way by exploiting the independence of the xi's, the amount of money that everyone brings. 6n, okay? So now, because there are n terms here, right? There are n terms here, and each one of the variance I told you is 6. Yeah, I told you here. This is not in the book, okay? There's nowhere, there's no reference for this, okay? You can look at my notes later on. Okay, I think it's okay once in a while to have something that's not in the book. All right, so now we want to compute the variance of S. What do we have to do? Use the formula, expected value of the variance of S given n plus variance of the expectation of S given n. But we have already prepared everything inside. So this is expected value of 6n plus variance of 7n. So now we just have to contend with what is variance and expectation of n. So our n is this particular random variable, which is called the geometric random variable with mean 10. Now, it is known that for a geometric random variable with probability of success 1 over p, right? The expectation is 1 over p. Okay, so this is 10 here. Okay, and the variance of n is actually 1 minus p over p squared. That is the variance of a geometric random variable. So basically, I just have to replace p by 1 over 10, which is the probability of success, 1 over 10 quantity squared. This is 90. Okay? Sorry, I did a bit of squeezing there, but hopefully it's clear. So these are the statistics I'm interested in, that I need to use later on. Okay? So coming back here, expectation is linear, so you can take out the 6. And what is this? How do I tackle this? 49, thank you very much, variance of n. But now I've already gathered all these numbers, so this is 6 times how much? What is expected value of n is 10 and 90 here. 10 plus 49 times 90. Okay, this is some number. The exact number is not so important, but the method to do it is much more important. Is this clear? Actually, I have very few things to talk about. So as you can see, the last few lectures, I'm doing a lot of examples. Actually, we can finish today. But we still have one more lecture, which is Tuesday. There's no lecture on Thursday for some reason. But I think Hadrian knows the answer, why there's no lecture on Thursday. I don't know what day is it also. Who told you that? How come I don't know? I just given the instruction not to teach on that day. All right, so does everyone understand this calculation? Can you see that I'm going very slowly? I will give some instructions because I told Sean actually asked me to do a Zoom tutorial consultation, yeah. Because all of us are already very well. So I will do a Zoom consultation / tutorial. Everyone understands this calculation? First, we need to prepare our statistics, which are these things here. So we have prepared them here, and we have prepared them here. Okay, and we need the expectation and the variance of the geometric. The expectation of the variance geometric, either you derive it from scratch or you remember the formula. I remember the formula. I can also derive it from scratch, but I don't expect you to remember this. But whatever you do, the mean is this, the variance is that. Okay, so that's the mean and the variance of the number of people who show up to class. Okay, then we need to basically plug this in here. Okay, so the 7 comes out here, it becomes 49, which is the square of 7. And we have left with 2 numbers here, here. Okay, then we just do some arithmetic. Ken? Any questions here? All right, so we have actually come to the final part of the lecture series. And the final topic I want to talk about is the central limit theorem. Okay. Because I've been asked to talk about this. I want to talk about this, yeah. Because there's a so-called syllabus that I have to go through for all the engineers here to be accredited, and you need to know this. I find this a little bit out of place, but this is very interesting. I use this theorem every day. Okay. I use this every day to do my work. All right. So I know this very well, and it's very powerful, very important. This is also in my 2 books. All right. So it's worth knowing. Are you interested to read my book? No, can understand. All you need is a little bit of probability. All right. So in order to prove the central limit theorem to you, let me share screen this. Let me share this screen. Okay. So can the people in Zoom see? Can the people in Zoom see my MATLAB? Okay. Can the people in Zoom see my MATLAB? Do you think there's any response? I responded already. Someone, I cannot see the thing. Okay, but so what am I going to do? All right. So first and foremost, let me set things up a little bit. I don't know whether you all know this language or not, but it's kind of similar to Python. Okay. So now what I'm going to do, let me just set up some numbers first. I'll explain what all these numbers mean in a moment. But this was how I was taught. Okay, very long time ago. I will explain to you what I mean shortly. Theorem 1n times 10. Okay. I do not know whether you know all these things or not, but this is a random number generator. Okay. So here what I'm doing is I'm generating n numbers. Can you see or not? A bit small, right? Here I'm generating n numbers, capital N numbers, which is 1000 numbers in the interval 0, 1. So let's see what this evaluates to. So here basically we have generated 1000 numbers, and all these numbers are basically between 0 and 1. Okay, so these are just random numbers. Now I'm going to multiply this by 10. So these are random numbers from 0 to 10. Okay, so these are random numbers from 0 to 10. Cool? Now this seal here is the ceiling. So what this means is that, okay, I'm going to round everything up. So I'm going to round everything up. What will I get? Let me show you. I will get numbers from 1 to 10, like this. All right, so I have 1000 numbers from 1 to 10. How many ones do I have? Okay, how do I calculate number of ones? Some and some, one moment. Let me call this vector A. Okay, so how many, so A is this. How many ones do I have? Sum A equal 1. Okay, I have 85 ones. Out of 1000, I have 85 ones. All right, how many 2s do I have? This number. How many 3s do I have? I have this number, 4. And how many 10s do I have? So as you can see, pretty uniformly distributed, as it should be. They are pretty uniformly distributed. Actually, we can do hist A like that, in order to see that they are pretty Does this come out? Okay, so that's the histogram of the numbers. It's pretty uniform. So I'm basically doing a PMF from 1 to 10. All right, and this is the realization. Probability mass function. All right. Basically, by this command, seal ran 110 or this one, blah, blah, blah. I am generating 1000 samples from a PMF that is uniformly distributed from 1 to 10. So the PMF looks like this. So the PMF looks like this. 1 to 10. 1. This is 110. 2. All the way up to 10. Okay, so roughly there should be 1/10 of 1s, 1/10 of 2s, and we notice that, yeah, there are 106 due to some statistical variation. Okay, we can also calculate, say, number of 7s. Okay, roughly 100. Okay, So what I'm going to do is to MATLAB prove the central limit theorem to you now. Okay, but here this one sample cannot do the job, so we need to do a little bit more. Okay, so what I'm going to do is the following. All right, this is set up like that. So you know this 4 thing, 1, 2, M. Okay, right. So what is this? This one cannot. It won't work like this. What am I doing here? All right. So I am doing what I did just now over 100 times. All right. So I'm generating 100 vectors of samples of 1,000 samples, where each one of the samples is a number from 1 to 10. Okay, so let's say this is a bit smaller, 10. Okay, so you can see that this is a matrix here. Samples is a 1,000 by 10 matrix. I'm just basically doing this many times. Okay, so now, okay, what do you think will happen if I do this? Okay, so what is happening here? All right, just now you notice that when I just generate one vector of samples, we have about how many? Let me go up. We are going to have, okay, sorry. We are going to have about 1/10 of tens, 1/10 of ones, 1/10 of twos, and so on and so forth. Okay, 1/10 of each number. Now I'm basically generating many of such vectors, and I am summing them up across the second component. Okay, so initially I have the PMF given by, as I mentioned, 1, 2, ... up to 10. Okay, that was a PMF or P, say X of X here. Okay, so by doing this operation here, what I'm doing is I'm looking at how many samples I have, all right, of a certain value. Okay, so just now in this particular variable, okay, samples ... 1. Okay, sorry. So just now in here, what we have was a bunch of ones and a bunch of twos and so on and so forth. Okay, here I'm summing over various sample vectors. Okay, so on and so forth. So now these are not exactly ordered in this particular way. Let me just erase this for a moment. Okay, so maybe we have in samples vector 1, we have 1, 2, 3, 4, 5. Here we maybe some other way, 2, 1, 4, 3, 5, and so on and so forth, all the way to 10 maybe. So I'm now summing like this, in this way here. Okay, so what is the minimum value of this sum? Well, the minimum value is 10. And it happens if all these are equal to 1. All must be equal to 1. Okay, and the maximum value is 100, is when all line up to be 10. But the extremal values are very rare. You need to have all 10s, you need to have all 1s. The middle values seem to be more likely. Okay, so that's exactly what this operation is doing. So now, having explained all these components to you, let me plot something. And like this, we do this first, and then we can make the picture look better. All right, let's look at this. All right, so we get this shape here. Okay, now this looks suspiciously a Gaussian. All right, but let me adjust this a little bit. To make this look a little bit better. This should be here. Uh, 0.5 hist A. Sorry. So as you can see here, this looks suspiciously like a Gaussian. The extremal values are small, and basically the center values are large. Let me try this again. Okay. Okay, so this seems to look like a Gaussian. So this is a sort of demonstration of the central limit theorem. We can have more bins here, say 20 bins here. Okay, so this looks a bit like a Gaussian PDF. And indeed, what we will state later and what we will use is basically the central limit theorem. Okay, so the central limit theorem says that if you average a bunch of independent objects with the right normalization, you get to a Gaussian. Okay, so this can look more like a Gaussian if you increase this. This is not quite. This is due to some statistical variation, I guess. Yeah. The more you have, the more it will look like a curve. Okay, it's not quite a Gaussian, but we don't have enough samples. Okay, but if you have enough samples, the so-called central limit theorem will tell you that you will converge to a Gaussian. So we will try to state this more formally, but this is something that is believable. Okay, the far ends are very rare. Okay, the middle has a lot of mass. All right. So that is my little bit of programming. I'm not very good at this, but you can see some things happening here. Okay, so we can maybe reduce this and make this a bit more. I think that will look better. I think something is wrong here. It's not very good. It's too concentrated. Something like that. Okay. So now let us try to state the central limit theorem properly, and let's see how we can use it. That's more important. Okay. Sure. I don't know whether you have encountered this before, because last time I kind of encountered this before when I was in school. We use the central limit theorem to do things. But let's just try to learn this from scratch. Okay, so the setup is as follows. Central limit theorem says that it's a very, very general result that says that if you have a bunch of independent particles or objects and you average them, then some limiting behavior emerges. And that limiting behavior is that of a Gaussian. Okay, so let x1, x2, x3, ... be a sequence. Sequence in mathematics means an infinite collection indexed by the integers. Infinite collection of objects indexed by the integers. A vector, you may have heard of a vector. A vector is a collection of numbers, a finite collection of numbers. A sequence is an infinite collection of numbers, if you wish. Okay, sequence is a technical term. Sequence of IID. Now I'm going to explain what's IID in a moment. Random variables. Let x1, x2, x3 be a bunch of IID random variables with mean and variance respectively. Mu equals to expected value of x1, and sigma squared is the usual definition of, is the usual symbol for variance, is variance of x1. So there are a few things here that you may not have encountered before. Now this thing here is called IID. IID is very common. It stands for independent and identically distributed. independent, we have come across this term. That means all these things are independent. Okay. Identically distributed means all of them have the same distribution. In particular, all of them have the same mean and all of them have the same variance. They are not replicas of each other. X2 is not equal to X1. But the PDF of X2 is equal to the PDF of X1. Okay? So if the PDFs of two things are the same, then their variance and their expectation must be the same. No two ways about it. Yes. Okay, let me show you. Okay. What do I mean by this? A lot of people are confused by this, but I'm very clear about such things. Okay. Suppose we only have two objects in our sequence, X1 and X2. Okay. By saying that they are the same, we mean that X1 is equal to X2. This means that X1 is the same as X2, or X1 is equal to X2. All right, that's what we mean. That means, let's say everyone's exam marks is captured by Xi. Your exam mark is X1. Oliver's exam mark is X2. If X1 is equal to X2, it means that your exam mark is definitely equal to Oliver's exam mark. Then are the two exam marks independent? No. Very dependent. In fact, if I know your exam mark, I know Oliver's exam mark. That is what this means. Now, another notion is, okay, their PDFs are the same. PDFs of X1 and X2 are the same. Okay, so your PDF of exam mark is the same as Oliver's PDF of exam mark. In particular, the means are the same. Okay, both means are 80. Both variances are 10, say. Is your exam mark the same as Oliver's exam mark? No, not necessarily. It could be. If you all copy each other, yes. But if you all copy each other, it's not independent anymore. All right. But if say you're doing your exams individually, that is independent. But perhaps you all study the same amount, so your expectation is the same. Is this clear? These are two very different concepts that a lot of people have confusion about. If the random variables are the same, they are far from independent. They are super dependent. But you could have random variables that are independent, but have the same PDFs. Like every coin toss, every toss of an independent coin, they have the same PDF or PMF, but the sequence, everyone is independent. Every toss is independent. Just like your exam score and Oliver's exam score, you could have the same PDF, but if you do the exam, you get independent marks. Okay, good. Liao Xue, is this clear? Okay. Right. So that is the meaning of independent and identically distributed. They have the same distribution or same PDF. So this one, identically distributed, refers to this situation here. Okay. So now let us try to understand a little bit more. Okay. So suppose we consider the random variable Mn, which is the average. Okay. Now, everyone in the whole class has a certain exam, say everyone IID, everyone studied the same amount. Okay. Everyone average is 80. Okay. Now, if my class is very large, what do you think this looks like? This number here, when n is very large. So all the random variables have mean 80. What do you think this number will look like as n is very large? Close to 80, right? You're averaging a bunch of numbers whose means are 80. Kind of, we are going to get there soon. Okay, so this is known as the sample mean. This has a name. This is some statistics thing, okay? It's known as a sample mean. Now, the sample mean is a random variable because it's a function of n random variables. Is a random variable. What is its mean and variance? Okay, after I answer these questions, we will understand what Liao Xue is trying to say. Okay, so let's consider the expectation of the sample mean Mn. So we have to do expectation over 1 over n x1 dot 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 xn. Okay, by linearity, we can bring the expectations inside. Okay, but each one of these guys here has expectation mu plus dot 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 plus mu, and there are n of them, so this is mu. All right, so the sample mean is exactly the mean. Okay, that's a point. Okay, so what about the variance of the sample mean? The sample mean is a random variable, so we can compute the variance. So by the same token, we have variance of this guy here. So we can basically compute, we can put in the variance in here. Okay, so what do we do here? There's a factor of 1 over n. Can we bring it outside? What do we have to do to compensate to bring it outside? Yes, 1 over n squared. And we have variance of x1 plus dot 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 plus variance of xn. Okay, so that becomes 1 over n squared. Now the variance of each person is the same. It's called sigma squared. All right, so we have sigma squared plus dot 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 plus sigma squared. Right? Now, how many sigma squares are there? N, but we have n squared there, so we have to cancel 1. We have sigma squared over n. All right, so the point here is that as n becomes large, the variance of the sample mean vanishes. Vanishes means converges to 0. Okay, this one becomes very small. This one becomes super small. So the picture is as follows. Okay, now I'm going directly to section 5.3. If you're interested, you can read section 5.1 and 5.2 on the weak law. Weak law is something that I teach in some other class. Right, it's not very difficult, but we are not going to talk about that, right? Because previous classes don't teach that, so I don't want to teach extra. So, but the picture is as follows, all right? We initially have a certain PDF. Okay, let's say we are in continuous land, and we have the PDF that is centered at mu and has a certain variance. So maybe our PDF looks like this. It need not be Gaussian, let's say some random variable. Okay, it looks like this. Okay. Let me draw something else. So we can have some PDF that looks like this. So that is the PDF of x1, one random variable. Okay, that's our PDF of one random variable, and the mean is somewhere here. Oh, shucks. Okay, the mean is here, and there's a certain variance. Now, as I average more and more, okay, so this is going to be more and more sharp. But we are still at the mean. This is the PDF f of M10 x. 10. We are averaging 10 students. We are averaging the exam score of 10 students. Then they are more peaked at mu. The variance becomes smaller because by this formula, the variance drops by 10. Okay, but I cannot illustrate dropping by 10, factor of 10, so I illustrate becoming thinner. The variance compress. Okay, now as n becomes even larger, then this is going to concentrate much more. Maybe use this color. Okay, now at 100, oh my goodness, this is very difficult to draw. We are going to concentrate to here. This is what I do for a living, you know, finding how fast we concentrate. So basically, as you increase the number of students, the mean gets closer and closer and closer to 80. Because we have more evidence, all right? Now, there's a mathematical way of talking about this. Yeah, this one. converges to 0. Okay, so the variance converges to 0. Initially, the variance was respectable. That was the initial variance. Then the variance became smaller. The variance now became sigma squared over 10. Actually, what we are drawing here is in fact the standard deviation. Okay, so we need to do this divided by, say, square root 10 here. Now, after we average 100 times, this is sigma over square root 100, which is sigma over 10. Becomes very small. We concentrate to 0. Okay, so this is pictorially the weak law of large numbers. I teach this more properly. You can watch my YouTube videos. Yeah, this is called a weak law of large numbers, but there's a more proper way of saying this. There's also something called a strong law of large numbers. Okay, all right. So let me just put a comment here before we take a break. The sequence of sample means, which is Mn, converges. Converges means get closer and closer to mu. All right. So there's nothing interesting about this behavior here because we basically get towards the delta function. If you know signals and system, we get to the delta function. That means we're not converging to any particular interesting distribution, not Gaussian. So what can we do to make this more interesting? That will be the subject of our discussion after the break. And we'll take a 10-minute break. We'll come back at 3:12. Okay? See you. Let me pause the recording and stop. All right, we only have a few more things to say. But here, basically, I showed that the sequence of sample means converges to mu. Now, on the other hand, consider Sn. Sn is the sequence of sums. That means I'm basically summing up all your exam scores. Do you think that converges to anything meaningful? Well, so we know that that is nothing but n times Mn. Well, the sum is basically n times of the average. Okay? And it is easy to see that the expectation value of the average grows n times mu. And the variance of the sum is also n sigma squared. So the sum diverges. Diverges means becomes very, very large. Diverges to infinity. Okay. It does not converge to anything. Possibly negative infinity, but I don't think you all will have any negative exam scores because I have no negative marking. Unlike when I taught EE2012A, I asked them to do negative marking, okay, and they really did. Because so this one is positive, okay, let's say this is positive, okay, so diverges to infinity, it does not converge to anything meaningful. Okay, so we have one case of Mn converges to mu, but the distribution of Mn converges to a spike. Okay, so it's not meaningful. On the other hand, if we just consider the sum and we don't normalize this by anything, then this sum diverges off to infinity. So these two extremer cases are not interesting. So what will be interesting is the following. Consider instead Zn. That's why in central limit theorem, this is called the z-score if you wish, or z normalization. There's something like this in Python, all right? So we have the sum minus n times the mean divided by sigma square root n. This is x1 plus dot 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 plus xn minus n times the mean divided by sigma square root n. Okay, so it is easy to check that expectation value of Zn is equal to 0. Okay, why is this 0? We can bring out the constant factor and we have expectation value of Sn minus n mu. But expectation value of Sn is exactly n mu, so that's 0. the variance of Zn is equal to, well, the variance of 1 over sigma square root n Sn minus n mu. Okay, well, you have to bring out the sigmas here, 1 over sigma squared n. All right, you need to square it. By now, you should know. And this is the variance of the sum of n random variables xi minus mu. Okay, now the variance does not depend on the shift on a constant. So this becomes variance of sum I running from 1 to n of xi. But this is nothing but 1 over sigma squared n times n of variance of x1. Okay, so you have something very convenient here. The n here cancels, the sigma squared cancels, and you are left with exactly a 1. So the point is that if we normalize in this way, particularly the square root n here, these random variables, mean and variance, they are always unchanged for each n. Always unchanged. All right. So the point is that this being 0 and the variance of Zn being 1 stays the same, stays unchanged for all n. All right. Thus, this sequence of random variables Zn, sequence because the n will increase. Basically, I take away the mean and I divide by square root n. Thus, Zn has hope. Let me just put in quotation marks. Has hope of converging to something meaningful. Notice that in the previous two examples, right, of me just taking the sum, the variance blows up. Okay, here the variance goes to 0, not meaningful. Here the variance stays invariant. It's basically staying at 1 all the time. So there's some hope of this actually converging to a particular non-degenerate distribution. Okay, and this is the essence of the central limit theorem, right, which is stated more formally as follows. And actually, you don't need to know how to prove the central limit theorem. You don't need to know how to state it properly. You need to know how to use it. All right, and we'll see how to use it later on. But I cannot say how to use it without stating it. The central limit theorem. Okay, there's some history behind all these things, you know. Every so-called theorem in mathematics was discovered by someone. Okay, this is not discovered by me. Otherwise, I'll be super famous. This is discovered by Gauss in the late 17th century. Okay, and this is not very difficult to prove also. But I didn't talk about moment generating function, which is the last part of section 4, chapter 4. If I did talk about moment generating function, then we can do this very easily. Okay. So the central limit theorem is as follows. We have x1, x2, ... It's a sequence of IID random variables. And they all have the same mean, mu, and they have the same variance, sigma squared. So I just have to specify the mean and the variance of the first object. Now I create the random variable Zn, which is basically the sum of these random variables, take away n times of the mean so as to make it 0 mean, and divide so that I make the whole thing have variance 1. Then the central limit theorem says that the CDF of Zn converges to that of a standard Gaussian. This is a super important result. Okay. So this means mathematically, for all real numbers z belonging to R, okay, then the CDF of Zn, which is the probability that Zn is less than z, converges, that means looks like phi of z, which is this 1 over square root 2 pi e to the minus u squared over 2 du. Okay? So Here are some remarks. This is incredibly general. Remark. The PDF or PMF of the xi's can be anything, as long as they have the means and variances given by mu and sigma squared respectively. Can be anything. So it doesn't matter what random variables you started off with. You could start off with some very wild random variables like the ones I showed in MATLAB. It's basically uniform. Or you can start with exponential random variables. You can start with Poisson random variables. And if you do this averaging and subtracting off the mean and dividing by the standard deviation, normalizing by root n, the limiting behavior is always that of a Gaussian. If you have a lot of so the analogy is, if you have a lot of particles in the sky, then their ensemble behavior is like a Gaussian. If you have a lot of students, say we have more than 100 students in this class, then very likely, even if I don't want to grade you on a curve, I will grade you on a curve, because the law of large number or the central limit theorem says that the behavior of your exam scores will be on a curve. There will be some people who do very badly. And it's explained by this. So, why do we grade on a curve? It's because of the central limit theorem. Right? So if we got some people, all right, if we have enough people, then you will be on a curve, and it's explained by the central limit theorem. Okay? So, how do we use the central limit theorem? Here's the procedure. After I outline the algorithm or the procedure, we will go to examples, okay? So the normal approximation, normal is a Gaussian, all right? Normal means Gaussian. Normal approximation based on the CLT. CLT is central limit theorem, okay? Right, so we have the sum, which is x1 to xn. We're going to call that Sn. So the xi's are IID, random variables. And how we're going to use it is the following. If n is large and we are interested in the probability that Sn is less than some value c, then let me write this in proper English. If n is large, then this can be approximated by treating Sn as normal, as a normal random variable or Gaussian random variable according to 1. Okay. Calculate the mean and mu and variance and sigma squared of Sn. Okay, so those are the mean and the variance. And point number 2 is calculate the normalized value of C. Calculate the normalized value, which is called Z, take away the mean, divided by sigma square root and divided by the standard deviation. 3, use the approximation. Probability and we are interested in this probability. This is approximately phi, which is a Gaussian CDF, and you have tables for that of Z. Okay, so that is the whole algorithm, the whole procedure. You are interested in this particular random variable being less than C. All the x's are independent. Suppose you do not know the central limit theorem, what would you do? Liao Xue, what would you do? Suppose you didn't know the central limit theorem and you want to calculate this, which is the probability that x1 plus ... plus xn less than c. How would you calculate this exactly? No. It starts with c. So you have all these random variables that are independent and there's a sum. Let me ask someone else. John? So all these people here are independent, and we are say we're only interested in probability x1 plus x2 less than c. What will we do? We don't know the central limit theorem. we will do something that starts with C. These two guys are independent, and we are interested in some behavior of the sum. How do we get the density of x1 plus x2? Convolution. Remember, if you have x plus y and x and y are independent, you get the density of x plus y, the probability density function of x plus y, by convolving the probability density function of x and the probability density function of y. Now, so if you are interested in the probability of this less than c, you can, in principle, convolve the density of xi n times. That is the kosher way of doing it. Kosher way. Yes, you integrate n times, but that's a very pain in the ass, right? Right. So this is a quick and easy way of avoiding all the convolution. But that is actually the best, the standard way of dealing with the probability that x1 to xn less than c, right? You do convolution n times, but that's very painful. So we want to avoid all this pain. And so the procedure is we calculate the mean and the variance of the Sn, we calculate the normalized version of C, we call it Z, and we do this approximation because we are pretending that this is Gaussian. And so this, what we are going to do here is we're going to take away n times the mean divided by square root n variance less than Z. The Z is basically the normalized version of C. And we are pretending that this is Gaussian, so we can replace this by phi of Z. So that's a quick and easy approximation. Okay? All right. Understand? Okay. So let's do a couple of examples. Example 1. Okay. So we are going to load a plane with 100 packages, and each package is of weight xi, uniform from 5 kg to 50 kg. Okay, so here's the picture. So we have this particular PDF of each random variable xi, and it's uniform from 5 kg to 50 kg. So we are basically going to put packages in a plane, and this is 1/45. Hopefully you can see. All right, so each one of these is the probability density function of the weight of a particular package. All right, so while we are interested in the probability that the total weight on the plane exceeds 3,000 kg. Okay, let me see. Yeah. So this is certainly feasible in the sense that, well, this is going to be some interesting number because the maximum weight is 5,000 kg. The minimum weight, is it 5,000? 50, yeah. The minimum weight is 500, the maximum weight is 5,000. So this is in between. This is meaningful. You are loading packages onto a plane, and each package is between 5 kg and 50 kg. Okay? What is the chance that the total weight is more than 3,000? Right, so let's set this up. Okay, so this is the probability that x1 plus dot plus x100 exceeds 3,000 kg. Do you agree? Now, how would you compute this in exact form, not approximate form? You would convolve this thing 1,000 times. Or 100 times only. Yeah, 100 times. Okay? But that's very painful, you know. Very painful. You convolve these 2 times, it's already very painful. Right? Because I think my student tried to convolve this 2 times. Take 2 of these and convolve together. It's already very painful. You convolve this 1,000 or 100 times, you will not do it by today. All right? By hand, you cannot do it by today. But nevertheless, we can do this very quickly. All right? By the central limit theorem. So we call this S100, the sum of the 100 packages. All right, what is the procedure? the procedure is calculate the mean and the variance of Sn. All right. So the mean of S100 is basically 100 times expected value of X1. So what is the expected value of X1? Well, it's basically the average of 5 and 50. Okay, so that is 27.8. It's basically 100 times 27.5. We'll just leave it like this. All right. So what is the variance of the S100? It's 100 times the variance of X1. 100, well, this is uniform. So by now, you know, B minus A squared over 12, right? Times 45 squared over 12. So this is basically 100 times 168.75. All right. So we compute these statistics first. Then we can now calculate this one here. We can now approximate. So this one here, all right, this is going to be equal. Okay, before that, we're going to calculate the Z score. Okay, so our C is this guy here. So the equivalent Z is C minus 100 times 27.5. This is 3,000. Divided by what? Square root of 100 times 168.75. So that is the Z. Okay, that is equal to 1.92. Okay, right? So the procedure says that you take away the mean, you divide it by the standard deviation multiplied by the total number of times. Okay, so this is then approximated by the Gaussian evaluated at 1.92. Okay, not quite, because this is less than this. Then it's 1.92 because the phi here, this function here, is defined as the integral from minus infinity to z. So you need to do this one first. We are going to compute this before we compute that. Okay, but this one we can look up the table, and it's 0.9726. So if we are interested now in the flip version, which is this version here, then this is nothing but 1 minus this version here, less than this. Do you agree? We have already evaluated the less than version. Now we want to evaluate the more than version, we take 1 minus. Okay, so we are left with 1 minus 0.9726, which is whatever it is. Okay. So the punchline here is, okay, there are some things to do. We want the probability of the total weight bigger than bigger than 3,000, right? But the standard procedure says we have to consider the less than sign. So what we are going to consider is the less than version here. But for the less than version, we need to calculate the effective Z score here. We take away n mu divided by square root n sigma squared. And I computed all this in advance. All right, then we put it into the calculator. The less than version yields 0.9726. So the more than version is going to yield 1 minus 0.9726, which is whatever number. Is this clear? So this is an approximation to the, actually this is an approximation here. That's where we are approximating. Okay? Is that clear? This whole procedure, is it clear? Andrew Wee, is this clear? So we take away n times the mean divided by square root n times the standard deviation. We get the effective Z. All right. And then we basically approximate the Sn with a standard Gaussian evaluated at Z. Is that clear? Now we are going to go to the most difficult example we can think of. Okay? All right. I can guarantee you the next one is very difficult. All right. But let me get through this and then we'll be quite happy. We have time to talk about this difficult example. All right. Okay. So now this example, you really need to think about what's happening. All right. I can tell you a story. So there is a machine, the machine. Actually, when I saw this example, I was very confused. A machine processes parts one at a time. Okay. The processing times for each part, processing times are independent random variables, uniform in the interval 1-5 seconds. So we are going to process the parts, and the processing time for each part is anything between 1 to 5 uniform random variable. Okay? And now we are interested in the probability that the number of parts processed within 320 seconds is at least 100. Okay, there are a lot of things, a lot of words happening here. All right. We are interested in the probability that the number of parts processed within 320 time units is at least 100. So we're going to give this a name. The number of parts that are processed within 320 seconds. Let's call this N320. So what we are interested in is actually this probability. Probability that number of parts processed within 320 seconds is bigger than 100. This is a difficult example, okay? It's non-trivial because you need some special thinking, okay? Right. Now, in order to compute this or estimate this probability, let us make things a little bit more formal. Let xi, which is uniform from 1 to 5. So basically, it has this density. Density is probability density function. 1, 2, 5. Okay. Let xi be the processing time of the ith part. Okay, right. So what we are interested in is basically this probability. But this probability has no xi. Right? Now we know what is the probability density function, the PDF of each xi. But we are interested in the probability that the number of parts processed within this number of seconds is at least 100. Okay. Now it makes sense at this point to define S100, which is the processing time of the first 100 parts. Okay, so this is the processing time of first 100 parts. Now, we are interested in this. How can we relate this to the x's? Because we want to apply the central limit theorem to this guy here. How can we relate these two objects? If the number of if the amount of time and what is N320 is the number of parts processed within 320 seconds is at least 100. Then what can we say about the processing time of the first 100 parts? What do you think? Okay. A lot of things happening here, right? That's why it's a bit confusing. Right, the probability, now we want the probability that the number of parts processed within 320 seconds is at least 100. Okay? And we have this notation here, which is the processing of the time of the first 100 parts. Each part is xi. No. Confused. Each part has this particular probability density function. Each part is processed with a time between 1 to 5. Okay. Okay. So the picture is as follows. If you cannot follow, let's look at the picture. Okay. This is the starting point. This is how long it takes to process the first part. This is how long it takes to process the first part and the second part. This is the time it takes to process the first 100 parts. Okay. This dot here. Okay. So we are interested in the event that the number of parts processed within 320 seconds is at least 100. Yes, total time allowed, right? So where do you, how do we express this? How do we express this quantity here? Can we simplify this in terms of the S? All right, so the claim here is that this is the same as S100 less than 320. Okay, why is that so? Suppose 320, suppose the time 320 is here. Okay, then what can we say? The number of parts that we service at time 320 is at least 100, right? By definition of the picture. Because we service 100 parts already before 320. Right? If 320, the time 320 seconds is here. If 320 seconds is here, before S100, that means we have not serviced 100 parts yet at time 320. We have not serviced 100 parts yet. Because the time that we service 100 parts is here to the right. Okay? There's a more formal way of saying all these things. This is again covered in my graduate class. Okay? But this is believable from the picture. One more time. All right? So here we are interested in the probability that the number of parts processed within 300 seconds is at least 100. We process at least 100 parts in 320 seconds. Okay, so 320 seconds is here. This is the time we took to process the first part. This is the time we took to process the first and the second parts. This is the time we took to process the first 100 parts. If this comes before 320, what can we say? At time 320, we process at least 1,000 parts, 100 parts. Right? Because by definition, S100, we have already processed 100 parts here. Right? Yes, because S is nice. Because S, we can use the central limit theorem, since S here is x1 plus dot 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 plus up to x100. Then we use the standard procedure. So what is the Z? Z is you take the 320 minus 100 times the mean divided by square root of 100 times the sigma squared. You find the equivalent Z first. So this is 320 minus 100. What's the mean of this guy here? 3. Very good. Thank you, Wikiet. What is the variance? You take 4 squared over 12. Right? 4 squared over 12. 5 minus 1 quantity squared over 12. Okay. So this is 1.73, the book says. All right. So we can estimate this guy here. We can estimate this by using the central limit theorem. Here, by the central limit theorem, that's where we're applying. This is the same as the probability, or this is the same as phi of 1.73. Which is 0.9582 from a table. You see, this problem is far from easy. If you think my class is easy, you are wrong. Because even I have to think here. You have to refer to this picture here. If 320 is here, we have not serviced 100 parts yet. We are interested to service, we are interested in the following probability in English, okay? The probability the number of parts processed within 320 seconds is more than or at least 100, which means the 320 must be here. If it's here to the right of S100, we are good. Understand? No. But this is how the book wrote it. Okay. Basically, you want to write this in a better way, right? Now, my exam questions are very clear, but this is a good example from the book, actually. Okay. So we have to turn this around from the N to the S. Because once we have turned it around to the S, right? The S is expressed as the sum of independent random variables, and we are good to go to the application of the procedure to find the Z. Once we found the Z, we plug into the phi, and we have applied the central limit theorem. Hey, there's a lot more we can say about the central limit theorem. I can talk about the central limit theorem for one whole semester, you know. Yeah. There are some things I cannot talk about for one whole semester. You're wrong. But I can talk about central limit theorem. There are people in NUS who devote their lives to the central limit theorem. They devote their whole life to showing better central limit theorems. So what I've taught you is the basic central limit theorem. Information theory, which is just an application of probability. You can read my book. Okay, this is where I will stop today. I've said everything I wanted to say. Next time, we will do a few more examples on the central limit theorem, and then we'll be done. Okay? I know, that's why. Yeah, that's why it's a bit painful. All right. Thank you very much for your kind attention.